Good morning, and thank you for joining Delta Computer Systems for another informational webinar this morning. Thank you all for attending. We appreciate this audience, and we're glad that you could be with us. Just a few housekeeping items before we get started. This session is being recorded and will be available in a number of places after the webinar is concluded, so that you can review or share with your colleagues. If you'd like to share the recording, that would be great. Also, at the end, we very much appreciate if you will receive a short survey. We would appreciate if you would fill that survey out. It lets us know how we're doing, but it's also an opportunity for you to share with us some topics that you might be interested in hearing about going forward. So if you would fill that out, that would be a great help to us. Today's presenter is Jacob Paso, the Motion Products Development Manager here at Delta. Jacob is heavily involved with technical support, and today Jacob will be talking about force control and tuning on a hydraulic cylinder using some demonstrations in RMCTools and using an RMC motion controller. So with that, I'll hand it over to Jacob.
Thank you, Aaron. Good morning, everyone. Today we're going to learn about force control and tuning on a live hydraulic cylinder. First, I want to mention that if you have questions, you can ask them in the chat section of the webinar control panel you have, and those will show up for us as questions. I will try to answer them on the fly if I'm able to. Otherwise, we have some panelists on board who will be able to answer your questions as well. Today, we will cover setting up a force axis, tuning a force axis, doing ramps, sine wave curves, position to force transition, force limit, and some more items. For more info on using RMCs, we have Delta videos on our website. We will go through the information fairly quickly today, so if you feel you're a little bit lost, you can review this type of information. We also have past webinars on our YouTube channel. That is Delta Motion Control, all one word. You can find us real easy on YouTube that way. And you see we actually have some of our past webinars listed here that you can use for refresher. I want to begin with talking about the main types of force axes that we deal with hydraulic motion control. First one is a hydraulic cylinder with two pressure sensors on it. We call this dual input force or differential pressure. Calculating the force based off pressure sensors is fairly easy because we just multiply the area of the piston times the pressure sensor. But we cannot just subtract the two pressures from each other because the inside of the cylinder has different areas on each side of the piston if you have a single rod cylinder. If you have a dual rod, then they're equal and you can just subtract them. Well, we calculate the force by multiplying the pressure times the area of side A and subtracting the pressure times the area of side B, and that gives us the resulting force on the rod. However, that does not account for seal friction, so we're not getting extremely accurate force. However, this solution is very rugged because the pressure sensors are back on the cylinder, they're away from the moving rod and load, and the wiring is very easy. It works very well in a lot of difficult situations. If we want more accuracy, we go with the load cell. The load cell is mounted out on the end of the rod, and that becomes a little bit tricky because we need cable management plus getting that mounted in there. So it's generally not as rugged, but if we need great accuracy, this is the only way to go with the load cell. Now, with either a dual input force or load cell system, we can add a position sensor to the cylinder, and now we can have better control on our force because we can better regulate the speed at which we encounter force, and in some advanced situations, we can actually add a velocity feed forward on top of our force control. It's also possible to do force control within a hydraulic motor, either force or torque, of course. That's not as common, but the concepts are very similar to what we're talking about today. So we're going to start with a live example. We have a hydraulic cylinder here that's running. You can maybe hear the hum through the background noise right now. 24-inch stroke, 2-inch bore. Four-way proportional valve, 100 liters per minute. We have 1 micrometer position sensor. And we have pressure sensors on this cylinder to calculate the resulting force. And we're feeding it with 1500 PSI pressure, which means the max force then is approximately 4,700 pounds that we're going to deal with. And with this system, we'll see that we can control the force within plus minus 3 pounds fairly easily. So that equates to about 0.07%, assuming I did my math right. And this is just a normal high performance hydraulic system. We haven't done anything real particular special. It's actually a bit more than 15 years old, and the valve is probably that old as well. And this is just what it does without any reasonable difficulty. So we'll look at the live system here. I have a webcam showing the system here. You can see the hydraulic cylinder. We have a manifold with several valves on it that we use for different training purposes. The valve we're using is actually not on the image here. Underneath the cylinder, we have a pressure sensor on this end and a pressure sensor on the other end. It's not possible to see those here. And we just have a block here at the end with a rubber block on it that we're going to run into and control force. And we'll be doing a little bit more besides that a little bit later. I'll move that down to the bottom of the screen here so we can see it move back and forth. And we'll open RMCTools as well. And we should be able to see both of those when we're running. So I'm connected to this RMC200 motion controller. If we look at the axis tools here, we see that we have one axis. We have position information, velocity, and we also have the force. If I go to the plots and start a trend, we'll do some motion commands just to see that we actually have a real system going on here. So I move it to 10. We see that it's moving. And in the plot here, if we turn off some of these items, I can explain what they are. So the target position, this is where we moved in position control. The actual position red is right on top of it. So we actually have really good control here. And let's see, here in the middle, we're falling within 0.003. We can look at these two values here. And at the end, if we look at the two values in the plot detail window, we see we're right on there. We can see that the target velocity during the move was this, and the actual velocity is following it quite well. Actual velocity is always noisy because we're calculating it from the position. The target force here doesn't really matter what it is because we're not controlling force. And we see the actual force, the black line. We can see the scale here. It's not much above 0, just a little bit. So it didn't really take much to move this. We see the cylinder hardly has any load. It just has a little teeny tiny plate that weighs a couple pounds. And we have the control output, that's our green signal. So what I did was make a little user program here that moves from position control into force control. Moves to 23 inches, but when it hits 18, it's going to send a speed at position command, so that when it hits 21, it's going to be at 2 inches per second. So this is just so it's slowing down before we actually hit that block. If you hit it really fast, it's really hard to control. And then once it sees the force rise above 500, we're going to enter force control, go to 3,000 pounds. And then these next two steps are just going to ramp the force between 1,000 pounds and 3,000 pounds. So not a very complicated user program. Plot manager here will run this. Let's see, start task command. We'll look at that program, position to force. So now we should see once I click send here, we should see the position start moving, and then the force will rise. We'll enter force control, reach the force, and then ramp up and down. I'll click send. And it looks like that's exactly what happened. We'll stop it. We see the position moved up here, the red line. And right about here, if we zoom in, we see the target force was hanging around doing whatever it was doing. It didn't matter because we were not controlling force then. But right here, we switched to force control and the target went down there. Now we see the target, the yellow line, goes smoothly up and ramps into position here. And the actual force isn't following so well. We could improve the tuning there a bit, but if I follow up here and go up and look at the target force was 3,000, and the actual force, oh, we're within 2.5 pounds there. And then we see that we ramped down, we stayed there for a while, ramped up, stayed there for a while. And you can see down here that the rod is pushing into the block. Force control isn't visually so nice because a lot of times things aren't really moving much, so it's hard to see it. You get to look at all these lines in the plot instead. So this is just a basic demonstration of the simple force control we can do. Go from position into force. I'll stop that here and move back to position before we continue. See the rod's now hanging out in the middle. So we're going to continue talking about how to actually set up a force axis so that we can make it control force like I just saw, and then we'll look at some more advanced force control topics as well. So first, we're going to assign our inputs and outputs to a software axis inside the RMC. Then we're going to configure the feedback, both position and force, to make sure that the RMC knows what sensors it's talking to. Then we're going to do the scale and offset, which converts the raw sensor data into real-life units such as inches and pounds. Then we'll tune the position control and tune the force control. And then after that, we'll do things like run curves and sine waves and so on. Let's see. We will go to the RMC, and I'll put this in open loop. I am going to go offline here. So I saved that controller, and we are going to go back online with the same controller and reset it to default. So this will be just as if you were setting it up after you got the RMC out of its packaging and wired up. So we'll right click here, reset controller to defaults. Takes a little while for the RMC to restart, and we'll upload from the RMC all those default settings. And now we have the RMC as if it was just straight out of the box. We see on the modules, I have the power supply CPU, and then I have a CA4, which does the control output. The S8 does SSI. The A8 does analog input for the pressure sensors. In the axis, we'll set up the axis definitions. I have a bunch of extra axes I don't need here. I'll delete those. And I'll change this one axis from being a servo position control to being position and force control. Click change, and we'll change the control loops dual loop. For the output section, on the CA4, it is wired to output 0. And the first feedback per position, that's going to the S8 module, input 0. And the second feedback, we're going to choose force dual input because we have 2 pressure sensors. And those are A8 slot 2 input 0, 1. Click OK, and there we have that. Click OK, and again, the RMC restarts when we apply the new axis definitions. We have to wait a little while for that to complete. So we now have configured the physical inputs and outputs to be pointed to this software axis 0 that we have. So if we look back here, that was the first step. Next step is to configure the feedback, both position and force. So we go over here to the parameters, and let's see, we had the position was SSI, 24 bits, gray code, and we have approximately 24 inches of travel. Force was 0 to 3,045 PSI on the sensors, and we have the cylinder diameters there. So we have SSI, I said gray code, didn't I? Yes. So gray code, 24 bits, And that's all the settings we need to set for that sensor. I can download that. And now to see if that's working, I should be able to clear the faults, clear faults, and look at the error bits here and see if they all cleared. Looks like they did clear, so I must have that one set up right. Then we'll go down to the secondary control setup. That's the second input, the force. And this is just voltage plus minus 10. That's the only setting I need to set up to tell it that the sensors are connected. And of course, it was already that way. So we see the error bits are off. So that means that the sensors are connected and configured correctly. Next step is the scale and offset. So we'll go look at that. We'll go to the position scale offset wizard up here, click launch, and we have the transducer information. It's a linear transducer. And we're going to use inches as a position units, 1 micrometer resolution. And for the offset, we need to move the cylinder to some position where we know its value. Right now, the cylinder is fully retracted. We can see that in the camera down here. And I'm going to call that my 0 position, and I click the use current value to get the raw counts. Now, normally you'll see some counts here, but we have a little problem with this cylinder. The last 1/8 inch or so, it actually doesn't give us any counts, but it's such a small area, it doesn't really matter here. And 4, we need to say which direction the position units are going to go relative to the counts. I get my new scale and offset. And now there's some settings I may want to change if my position settings change, like the positive travel limit. We can throw it to 24. We want to put it beyond the end now if we're going to do force control. So we should be all right with that. Click finish. We have the new settings in yellow. Yellow means I need to download it to the controller. So that was the position scale and offset. I can check it out by going to the plots, running a trend. Let's see, I need to fix that there. And if I do an open loop move, axis not enabled. Need to put that in run mode and then everything will work. Click send. So now I see my axis is moving with an open loop voltage. Sure enough, I see my position is increasing. My velocity looks good. Let's see when it hits the end down here. You can see in the camera, hit the end, and we're at about 21 inches. So that looks about right. So then I know my position was set up well. The next step is to set up the force scale and offset. So here, pressure force scale offset wizard, we'll click launch. And here we have the option of several different cylinder types. The most common one is the top one, single-ended rod cylinder. We'll choose that. Now I need to enter information for my pressure sensors. First, I want desired force units of pounds. And 2, the output values of the pressure transducers. They're 0 to 10 volts each. So it was already pre-populated there. And then 3, enter the pressures at those values. So at 0 volts, we have 0, and at 10 volts, we had 3045, and that was PSI. And channel B had the same, 3045. If you are very particular about calibrating your pressure transducers, this wizard now makes it very easy to put in different values for each of your pressure transducers. Previously, we assumed they were identical and it was very difficult to calibrate them, but that's a feature we added within the last couple of years to make this easier. So click next, and we have to decide which direction the force will be increasing. So if I look down at this video here, as I'm pushing into the rubber, I want it to increase. So that means when the pressure on the other side of the cylinder, the cap end increases, then the force becomes positive. So I choose the first item as channel A, cap end pressure increases, the force is positive, it increases. If we go backwards all the way and the rod end pressure increases, that will give us a negative pressure. Now I enter the cylinder diameters. 2 inches and 1.375 rod diameter inches. Click next. Now it calculates the force, scale, and offset values. And I can enter some values for the positive force limit, probably about 4,700, and minus, well, it probably can't go to 4,700, but we'll throw a value in there. I'm not going to really be doing minus control here. Finish, and that puts those values in here. Yellow means what we have is in the project is different than in the controller. So I click download. And let's see if we have everything working here. Error bits are all right. Our position was working. So we did the scale and offset. Now the next step is to tune the position. And we'll go to the plot manager tuning tab and just use a tuning wizard on this with auto tuning. Should work all right. I'll kind of whiz through this thing. It's fairly normal. I think the second move, 19, maybe I'll shorten that up a little bit here so we don't hit the end for sure. Watch the cylinder here as I click move to start. You see it moves to the starting end with an advanced open loop move. And so it's kind of at the start. Now I click the move positive. It does a shaky move. Click next. And then we move to start for the second move. You see the cylinder moves farther towards the end. Click move negative, makes a shaky move and gives us a plot. Click next, we get the model, and finish, and we get the gain calculator. So I typically pull that slider bar down to values that look, like they might be safe. And in the tuning tools, we'll set up some motion here. Move from 1 inch and 20 inches a second, accel and decel 100 maybe. The next move, we'll move out to 18. We probably do a higher speed there. Accel and decel 100. And I move to 1. And notice that we got a following error here. Look at the plot. It started trying to move, and then it halted, and we saw that error gave us following error. If we want to, we can go to the event log and actually see that error. Axis halted because of following error. That's because I forgot to set in the axis parameters the halts. We need to turn off the following error auto stop because we know we're going to get a following error in the tuning procedure. So let's see if this works better. We'll move to 18. Okay, so we see down here the cylinder is moving, but very slow. It's lagging way behind. So I need to crank up that gain, apply the gains. We'll do a move. That looked much better very quickly. Okay, let's see, right here, if I look at the position, we're following within 6 thousandths. If I get to the end here, it's off by 6 thousandths, gets in, take a little while for it to get in. Maybe I'll increase the gain, get some more control out of it there. And I'll actually go to the plotting here and change the plot time to 2 seconds so you can see the whole move a little bit better. Okay, so let's see, right here, we're following within 4 thousandths, and at the end, go move to 18 at 17.997 and gets into 18, fairly reasonable. So this looks like, reasonably decent control for the position. And so the next step is to control the force, or to tune the force so we can control it. Now, before we do that, I want to do a little review of the PI&D. If you look at our other webinar on position control and tuning, we'll have a more thorough explanation of PID and feed forwards there, but I want to briefly touch on them here as well. Position PID and force PID work very much the same way. So if you got the concept in one, you'll have the concept in the other. So first of all the gains we have, the PID and force feed forwards, they each give their own contribution to the control signal to the valve. We calculate that continuously, such as every millisecond. The proportional gain is the main gain of the system that we need to use. And we're comparing position here because it's easier to visualize, but it works the exact same way on force control as well. So the proportional gain, if our actual is far away from our target, it's going to give us a large effort. It's going to push hard. And as we get closer, we're going to push less and less. That's exactly how you and I would control a system if we're trying to move a block somewhere. As we're far away, we push hard, and as we get closer, we push less and less. So the proportional gain is the same thing on the force. If the force error is big, then it will give us a lot of control output. If it's small, it'll just give us a little bit. And the proportional gain is the main gain that we use during control of force. The integral gain is also relative to position, but it also takes into account time. So if we have a distance between where this block is and where we want it to be, then we push. But if it isn't going, then as time passes, we push harder. And if it still isn't going after some time passes, we push harder yet. So the integral gain, it pushes harder and harder the longer there is an error. The integral gain is really good for making up little teeny small differences, because if you have a small difference, the proportional gain will only give you a small value. But if you have a small difference, the integral gain will eventually give you a large value to make that up. One concept I really want to focus on the force control is the feed forwards. Recall from the velocity feed forward that if we have a typical cylinder with a four-way proportional valve or servo valve, if we give a control signal, we get a proportional velocity. So the control signal is proportional to the velocity. So for example, if we give 10% signal to the valve, we'll get a certain velocity. If we give twice as much signal, we'll get twice as much velocity. And if we give 3 times as much signal, we'll get 3 times as much velocity. So then the question is, you guys can answer this in your chat window if you like. If we want to go 100 millimeters per second with this system, how much control signal will we need to give? Well, it looks like Corey Wilson answered me before I even got finished answering it or asking the question. You win. I'm not sure what you win, but maybe you remember this from last time as well. So that's correct. We can tell how much signal we can give based on the velocity we want to go. So this is how it works for position control. Now, if we go to force control, it's going to be similar. But first, I want to show a graph of the velocity. If we have our target position here and our target velocity, remember the control output is proportional to the velocity, so we know we'll give a control output that's proportional to that. Now, on the force feed forwards, we have something called a force feed forward and a force rate feed forward. The force feed forward gives control output proportional to the target force. So if we are going to control to 10 pounds, it'll give us only a little bit. But if we're going to control to 10,000 pounds, it'll give us a lot. The force rate feed forward gives control output proportional to the target's force rate. So how quickly we're changing the force. The force feed forward is typically for pressure control valves, the kind where if you give it a voltage, it will give you a proportional pressure. The force rate feed forward is used for four-way proportional valves like we have on this hydraulic cylinder, and that most of our customers use for force control. This is not so often used with pressure control valves. Sometimes we have customers doing it, but a lot of pressure control valves, they can't actually control all the way down to 0. They can get close, but not real close. So normally we use four-way proportional valves. So that means we're normally using the force rate feed forward and not the force feed forward. So in most of your applications, you will not use force feed forward. Some of you may have applications where you use it, but most of the time we're just doing the rate. So if we look at a four-way proportional valve, If our target force goes like this and our actual force, hopefully controls fairly closely, then the force rate looks like this. The rate being the slope. So the target force has the highest slope right here, so it's highest there, and it's lowest down here. The slope is lowest there and lowest here, so our target force rate is lower, and it looks like this. So that means the feed forward, or the control output on this system, is proportional to that rate. So the rate has a hump there, and the control output is proportional. So this means that we can use a force rate feed forward for this system. If we look at what a pressure valve does, we have a force rate here, but the control output is not proportional to the force rate, it's proportional to the force. So on this type of system, you would use the force feed forward. So I know the force feed forward and force rate feed forward can be confusing, but this explanation should make it clear when you use it and when not. So now we actually get to the force control tuning procedure using the PID and feed forwards and so on. And the basic procedure we follow here at Delta is this one. We move the axis so it encounters force. So we move it out until we hit the force. If we try to enter force when the cylinder is just in open air, what's going to happen is it's going to try to make some force, but it's not going to get a force till it encounters something. So it will probably accelerate at a high rate and go slamming into something and cause all kinds of problems. So you always want to encounter the force before you enter force control. Then you want to set the proportional gain to be a very small value. If you're using pounds, then it should be 0.001. But if you're using tons, then it should be a factor of 2,000 different. So it can vary wildly what the proportional gain should be, but generally you want to start very small. Then you actually enter the force control, and we have some commands that do that. Then we increase the proportional gain, and then we use a tuning wizard. The proportional gain, of course, we need to move and get some plots. The tuning wizard looks at the plot and gives us some nice gains. So let's go look at what that actually looks like on the system. So we have our system down here, and we have position tuned. In the tuning tools, notice I have position tab and a force tab. So here we do the force tab, and down below I'm not into the force region, so I'll go to the command tool, do an open loop move into the end. I don't need to do an open loop move. I could do a closed move for that matter as well. Start a trend. So I'll start this open loop move, and we'll see that the force went up. So the force is actually maxing out right now, but I should be able to enter force control if I have a very small gain. So 0.001 is what we have here. So now this button here, I'll click it, called hold pressure force, and we'll see what happens. Oh, I got an error. Stop the trend. Let's see what it says. Auto stop force following error. Well, again, I forgot to set the auto stop. So in the auto stops here, we go to force following error right down there, change it to status only and download it. By the way, it's important that you set these back to a halt level that's safe for your machine. It's happened that someone has set halts to status only all over, and the machine has failed disastrously and caused lots of dollars of damage and lots of lawsuits, and it could have been prevented by setting these auto stops correctly. So these are in your interest to set correctly after you're done with the tuning procedure. So let's try this again. We'll move into the end with that open loop command. I'm now at maximum force, and I'll click the hold pressure force control. So notice that my actual force falls down here. So it's not controlling very well, but that's to be expected, being that the force is so small. Now I'm going to actually ramp the target force down a little bit because I don't want to try to control at the max. That doesn't usually work very well. So we'll maybe ramp down to 3,000 PSI like this, and I'll probably have to stop that to get this to work all right with the Okay, so we're at our target force is 3,000, actually is 1830. So if I increase the proportional gain sum, download that, we doubled it. Notice the force control is a little bit closer, and I can continue increasing this, and the force should control a little bit better and a little bit better. And closer. And now I can probably start ramping a bit. Let's see, we'll move this one down to maybe 500 pounds over a second. So I go to 500, and then we go to 3,000. Probably increase the gain a bit more. And I'm going to ramp a little bit faster because that stresses the system a little bit more, and it will give the tuning wizard more information about how the system behaves rather than just doing slow, easy motion. So at this point, when I have a plot and the force is following, reasonably well, I can go to the tuning wizard, tell it to use that plot, calculates a model, click finish, and the gain calculator now comes up. And let's say I have 0.02 on the proportional gain here. So I should be able to move that slider up to at least 0.02. So we'll move it up there, apply the gains, and notice that it calculated a force rate feed forward and no force feed forward, which is correct for this system. So now if I ramp to 3,000, ooh, it's controlling quite well. And then down to 500, that's controlling quite well as well. So at this point, we now have tuned the system, controlling reasonably well. Of course, it depends on what my machine requires. If I look up here and look at the target force and actual force, I'm overshooting by about 8 pounds there at the end, 6, 7 pounds. If I move on here, ends up settling to, well, that's within a pound. And as I go on, we're within a pound or two holding position here, within at least plus minus 2 pounds, looks like. So for most situations, that's pretty good control. I want to talk about entering force control. You saw in the tuning that we simply use the hold pressure force button. There's a few commands that we can use. The hold current pressure force command, which is the one that we just used in the tuning tool, but you can send that yourself separately. And then there's an enter pressure force control auto command, and the same with time and same with rate. I want to point out that the auto command is only intended for use when the axis is moving. If you use it when the axis is standing still, all kinds of bad things can happen. The other two, they can be used when the axis is standing still, and what it does is it enters force control and ramps to the specified force in a certain time or at a certain rate. The auto is really cool because it does it when it's moving. So the demonstration I did at the beginning where the axis moved into the end and then automatic transition to force control, that was the auto command. Things that the force control can do is once we're in force control, like we are now that we did tuning, ramp the force up and down. We can do sine waves. We can do custom profiles like curves, and we can do gearing. So I'm going to demonstrate a couple of those here. So we are now in force control, and if we ramp to pressure force control, I usually prefer the S-curve. Notice that we have the options of linear and S-curve. S-curve gives a smoother change. The linear with the sharp changes, sometimes that can introduce really sharp changes and control output signal to the valve, and that can cause us problems sometimes. But here I'll ramp down to 1500 PSI. And we also have different types of ramps. We can actually search for those here in the pressure force control. If we do a linear, some kind of test systems, you need to linearly ramp it over a long time to a certain pressure. We can certainly do that here. and fairly basic, just ramping up and down. Ramp down to 1500. We can do a sine wave. So if I look at the sine start pressure force command, the offset is the middle where we're at right now, 1500. We'll do an amplitude of, I don't know, 100, frequency of 1, and we'll just set this thing cycles of 0, means that it'll run forever. Click send, and now we see the force. It's doing a sine wave. We have this cool command called change target parameter, and we can change the offset. Let's go change that to 1800, and we'll change that over, we can choose over time or cycles or whatever. We'll choose over time, maybe 5 seconds. So now we should see that the offset is changing. So I zoomed out a little bit here. The sine wave moves up, and we can change the frequency. Let's go change the frequency to maybe 3 hertz, and we'll do that over 5 seconds as well. So now we see the sine wave over here is speeding up. And we can reduce the amplitude as well. Let's go reduce that to 20. We'll change that over 5 seconds as well. So in case you're doing testing with force profiles and sine waves, this works just fine. If you're actually doing really high frequency sine waves, then you have to go to something called adaptive amplitude control, which will probably be the focus of another webinar someday. But for these low frequencies, our regular tuning should be fine. I'll stop this sine wave. Oh, notice this, I got an error. That's because I used the sine stop and not the sine stop pressure force. So it told me that I didn't have a position sine wave. Curves, we can make curves of profiles. So let's go make a new curve here. X value of time, let's call it 0, and we'll start at 1500. And then we go 10 seconds and ramp up to 3000. And we can click around here and make our own little profile. Notice that some sections you can make linear. So I'll click this dot here, go down to the selected section, and the type, I'll choose constant velocity, and now I'll make a straight line from this section to this section. And this looks like a decent profile. We'll go download this profile. This curve is curve ID 1. And I'll right click here and split above and below so we can see the plot as we run this and see if we actually get the similar thing. Now I need to enter force control again because it kicked me out. So we'll move to 20. Let's see, I wonder where it was entered force. Was it 21? 21.1, 21.5. Okay, looks like that was a little too far, 21.2. So now we're in force control here. So I can now do the hold current pressure force command 19 over here in the command tool, click send, and notice in the plot now that force that was waving around is nice and solid, so it's obviously controlling it. And I need to ramp to the beginning value of the plot, which is 1500. So we'll ramp to 1500 over a second. Looks like it's there. I'll stop this, trying to start a new one so it changes the zoom a little bit. And now I'll do the curve start command, and that was the curve ID 1. And we'll click send. I got a problem here, command error. Oh, I did the curve start, not the curve start pressure force. Okay, so in real life, even guys at Delta make mistakes, by the way. Fortunately, these are easy to solve. We'll do the hold current pressure force to enter force control. Then we'll ramp to 1500. And now if I do the sine start pressure force command, hopefully this will work better. No, curve start, not sine start. Curve ID 1. Let's click send, and there we see it go. I'll zoom out a little bit here. Zoom out a little more. And there we see the profile going, and I'll stop the trend, and we see that that profile matches up with the curve that we did. So again, especially on testing applications, curve profiles like this work very well, but certainly there's lots of other situations that is useful. We won't talk so much about gearing. I don't have a really great application here for gearing, but we will talk about position control to force control. Remember I showed you first, when we do position control, then we can move to the end into force control. And we call it bumpless transfer. You know, there's tuning things we can use to make it really smooth in case there's a small bump. But let's demonstrate that as well. So to do that, we'll make a user program. And we'll move the axis to some position beyond where we know it's going to hit the force, like 23. We generally want to go to fairly slow speed when we hit the force. Going into really hard speed is really fast speed is really hard. So maybe 1 inch a second will be good. And then a link type, we wait for the axis 0 actual position to exceed some value, or sorry, the actual force exceeds some value. So wait for that to be greater than 500. And we'll add a step after here. And then we do the enter force control auto. And we'll tell it maybe go 2,000 pounds. I like the S curve, it's a lot smoother. And that should be enough for our user program. Just tell it to move, wait for it to exceed a position, and then enter pressure force control. So I'll download that programming, and we'll go to the plot manager, start a trend. Now I'll move the axis back a little bit to a decent starting position, maybe 16 here. So look at the video down here. We can see it moved back a little bit. Now I'm going to start that user program. We have to be in run mode first. Start task, that was the user program. So if I click send, we should see the cylinder move out, enter force, and control force. So I'll click send. See the cylinders moving slowly down here in the video. You see the plot, the red line's going up, and it gets there and looks like it entered force control. The target force came down, ramps up, and we're holding force right here. So not real difficult to do the basic position to force transition there. And of course, we can do all kinds of things after that. We could ramp force and sine and gear and so on. Next, I want to talk about force limit. Force limit is a little bit different than force control. What we do with force limit is we expect that we're in position control, but we're going to limit the force. So if we have a commanded position here that we want to move to in position, and then the axis starts moving in position control, but then it encounters some obstacle, that position will be stopped so we don't exceed our force limit, so that it's in position control but just isn't getting there because we're limiting the force. So I want to demonstrate this a little bit on our live system. So to enter or to enable force limit, we first need to tune up the system, and generally we do that in force control, which we've done already. And we'll make sure to move the axis back right now so we're not in control. So now I'll choose the command called set pressure force control mode. I can browse for it here as well, or actually a set pressure force limit mode there. Set pressure force limit mode. And we can choose a direction, whether we want to limit in the positive direction or negative direction or in both directions. So I'll use the positive direction here. I'll click send. And now we should be able to see in the status bits that the pressure force limit is enabled. There's another bit that says limited. So once we encounter something that's causing the position to slow down so we don't exceed our force limit, we'll see that limited bit turn on. So I will move the cylinder out to the end, and we should be able to see this happen. Let's see, I need to move it to the end, not to where it is. So 23, click send. So we see the force is moving, or the position is moving. There's just a little bit of force as it's moving right now because it's encountered. Now the force goes up, and notice that the force went up to target force and didn't exceed that. It overshot a little teeny bit. Notice the target position kept going until it reached 23, but the actual position stopped here because we have force limit active. And so now we're actively limiting force. And if I start a trend again and then move back to 16, we should see the target force starts coming down, and eventually it reaches the actual position, then the actual position follows down, and then we continue back to our motion to whatever position we command it to, 16 here. So we see the target is beyond there waiting for that. Now we're going to change this up a little bit. We're going to put a board in between here and move to position in force limit and see that it will stop at the board. And then with the board, we'll actually push it back a little bit and see how that works. So we'll insert the board in there. You should see that now in the video here. We have that board. And if I send a command to move to 23, send it right now. We see the positions going up. We can see it's getting closer to that board in the video. And now it hits the board and is pushing on that board. Let's see, what's our target force? 2,000 pounds. So that's a whole lot of force. So we have Aaron here managing the board. Aaron, I bet you can't really push that board hardly any, can you? No, it is solid. Okay, so if we ramp that target force down to, say, 200 pounds, click send right here, so you see that it ramps down in the plot. Now, AJ, go pull the board back, try to hold it a bit. Okay, notice that he pulled it back, and look at that, the force is still trying to hold 200, and the position is now dropped back a little bit. Let's stop that plot. We see the position went back here, and he's holding it right there. And now if he releases that, we see that the position goes up, and notice it's fairly noisy here and not real great control on the changes. Part of it's because this little metal plate bounces against the board because we're angling the board on it. But it does get back to trying to control the 200 PSI. Now we can do even fancier things than just the basic force limit like this. If we have an example of a ship that's at a dock, I don't know if anybody's done this, but someone was looking at doing this. Instead of having ropes holding the ship down to the platform, to the dock, we have this hydraulic system that holds a vacuum plate to the ship. And to control this, when we're holding the ship here, we have to let the ship move a little bit. So right here, we need low force, but as the ship moves from side to side, we need to increase the force or increase the force that way. So what we can do is do a force limit where we're trying to hold position, but if we get pushed out of it, we start by resisting with the low force, and then we resist with a higher and higher and higher force. So what we can do is define a curve that defines a target force based on the position. And so if we're close to zero, we just have a very low force limit. And if we go farther and farther out of position, we have a higher and higher force limit. So what this is going to do on our system is that if Aaron pushes the board, it'll be easy to push that force, but it'll be harder and harder to push it after a while. So this is a little bit hard to get the curve done on the fly. So I have a curve saved from my previous project here. Right there, force increase. So we see that at about 19 inches, and beyond, we are at, what is it, 150 pounds. And as he pushes the board, it pushes the position back some. And so as it goes to 18, then the force goes to 300 pounds. So it will rise like that as he pushes it. So I'll copy this curve from this previous project into the one that we're doing, into the curves here. Let's see there, and we'll paste that curve. So this is a force increase curve. We see it right here. And that's curve number 2. We need to download that. And let's see if we go back to the plot manager here. Now we need to send the curve start command. And that needs to be the curve start pressure force. But I need a transition rate. So this, I won't explain too much right now. But basically helps us get onto the curve if we're not exactly on the curve, which we're never going to be exactly on the curve in this type of situation. So we'll do a curve start pressure force. That was a curve 2. No, we need the curve start advanced. We need some special settings there. So that's 2. The master register is going to be the axis 0 actual position. And the options, let's see if I choose help. I need on the options, I need absolute curve alignment of 0, absolute match alignment of 2, and I want to extrapolate. So that's +2 + 8, that's 10. And again, I'm whizzing through this, but that's probably the topic of another webinar sometime, exactly how the curves work. And let's see if I did this right without horrible many mistakes. I'll click send. And looks like, let's see, we are at an actual position of 19.3 and our target force is 150. So if we go look at that curve, we were at 19.3 somewhere. Let's see here, 19.3, and we should be at 150. So hopefully things are working all right. So now AJ, if you push that board, you should be able to feel that as you start pushing, it's 150 pounds, and the further you push, the harder and harder it's going to be. Is that true, AJ? AJ's nodding, absolutely. So he's feeling that it's getting harder and harder. Okay, you can let that go. Okay, and so now let's stop that and zoom out here. I'm going to right click and show the second cursor. I'm going to trim out the beginning of the plot and the end of the plot. We'll right click and say create trimmed plot. That creates a new one. Now I can right click and convert to XY plot to see if the force changed based on the position. That's based on the actual position, okay. And we'll turn off some of these that we're not interested in. Let's see. So here we see, if I move the slider, you should see these squares move. They show where it was in time. So it started up here, and as I move the slider, the square moves down, and we'll see that that's exactly what happened. As a target position or the actual position changed, the target force changed in the same fashion as we had the curve. So XY plots are really cool for checking out those kind of things. So these are just a few things that you can do with pressure force control. You will note that we went through and set all of this up from the default settings in the RMC to get good control in position, force limit, doing some advanced things. So all this is possible. Of course, it helps if you have a lot of experience. To do, in relatively short order. Now, this system is very well controlled, so that's really nice. A lot of force control systems, and especially a lot of pressure control systems, can be very difficult. Like pressure control on a transmission, an auto transmission, where everything is changing inside of it, can be very challenging. But for a lot of applications, this is very similar to what you may be looking at. I haven't seen many questions come through yet. We're just about finished. If anybody has any questions, go ahead and ask them. Oh, and don't worry, you commented AJ is getting tired. Yeah, he was holding that for a while, wasn't he? So, summary, we can do force control with pressure sensors or load cells. We went through position force control, force limit, and remember we talked about, actually no, this velocity feed forward on a force axis, something I wasn't able to talk about. I was hoping to do it, but I wasn't able to set up a system that does it. That will be a topic for another future webinar. And if you have any questions on your force control, remember Delta Tech support is just an email or a call away. And one last thing, if you want a hydraulic design guide for tips on how to design your hydraulic system so it can control very well, you can sign up for that at deltamotion.com. It's on the front page, looks like this. It says free design guide. You can get a free copy just by giving us your contact and mailing information. Let's see, any other questions before we close? This is the last slide before we go. Okay, I see a few thank yous. Well, with that, this has concluded the hour of force control and tuning webinar. Thank you for attending. We really enjoy having you guys here. Oh, I see one question here. What are the benefits of using pressure transducers versus load cells? The load cells are a little bit trickier to mount. You have to be careful where you put them, and you also have to run the wire out to the load cell. So that wire is cable, it's moving all the time, so you have to deal with that. But if you need accuracy and you can mount them, then you typically want to go with the load cells. Pressure transducers, they can also calculate the force of the cylinder while it's moving because they're looking at the pressures in there. The load cell, it cannot calculate a force of anything until it actually has real contact. And so sometimes that makes a difference as well. And with that, enjoy force control and tuning. Goodbye.
Thank you so much, Jacob, and thank you to all of our attendees for joining us today. Just a quick reminder, you'll get an automatic link afterwards for a recording of this session. If you would like a little bit more produced recording later on, those will be available at deltamotion.com. Also in our discussion forum, if you look in our discussion forum, we have a webinar topic, and that's at forum.deltamotion.com. And then, as we mentioned before, we have a YouTube channel. It's Delta Motion Control, all one word. Thank you.